show us the magic you get to get a faculty position by giving a long talk, right?
I have to apologize, Andy. So as many of you might know, today was the first match in the World Cup, and my national team was playing, and they just found out that they lost 4-0. So
this is cricket, right?
Yes, yes. So I'm sorry if it's a little bit depressing, but I'll try to get the points across. So hello everyone, I'm Faisal Nawab, and I'm doing this work in collaboration with Divi Agrawal and Amr Al-Abbadi at UC Santa Barbara. And what we propose in this work is dynamic Paxos, which is a Paxos variant for edge applications. These edge applications where we have stringent latency and throughput requirements. And to satisfy these requirements, we push the resources, the compute and storage resources, all the way to the edge. However, this changes the landscape of the system model that we consider in the cloud. We start with data centers that are globally distributed around the world, but now as we push the computation and storage to the edge locations, we have many edge locations where we're hosting storage and computation. And this changes the landscape, and it adds hierarchy and locality that we can leverage in our systems. However, the current systems are not built for this environment. So if we take the Paxos protocol that we consider in this paper, and we run it, we find that it's a majority-based protocol, meaning that it needs to pull the votes of a majority of nodes. And this not only needs to pull nodes that are far away, but it's also a large number of nodes. And if we do this in every step in the protocol, this can be degrading to performance. So to combat this problem, we've observed a recent work, a recent theoretical work in Paxos, which is called flexible Paxos. And that was out 2 years ago. And flexible Paxos made a very interesting observation. So that observation is that the Paxos protocol proceeds in 2 phases. There is a leader election phase, where we elect a leader, and there is a replication phase where we commit the commands or transactions. And each one of these 2 phases requires pulling a majority of nodes. And basically, this is because we need to have an intersection between any 2 quorums. What flexible Paxos observed is that we can design the replication and leader election quorums in an arbitrary way, but with only one sole condition. That condition is that the leader election quorum must intersect with the replication quorum. So with that observation, what we can do in a scenario with 7 nodes, rather than a majority, we can have a really small replication quorum that only span 2 nodes. But the consequence of this is a much larger leader election route that spans 6 nodes. So that was great news for our application, because what we can do now is use flexible Paxos to have these small replication quorums all around the world. So now if I'm at California, I can just use the replication quorum that is closest to me. But of course, the cost of this, when I need to elect a new leader, it's going to be really expensive. And flexible Paxos didn't give us a solution to combat that problem. So we had an observation. And that is the main proposal that we do in dynamic Paxos, which is, can we take the nice features of flexible Paxos, which are the small replication quorums, but also decrease the size of the leader election quorums? And our observation is that the condition to intersect with replication quorums is not necessarily for all defined replication quorums that are all around the world, but we can only intersect with the replication quorums that are being actively in use. So for example, if I know that only these 2 replication quorums in Asia and Australia are being used, then I can know that it's enough for me to only intersect with these 2 replication quorums. And that is the basis of dynamic Paxos. So how do we turn that observation into an actual protocol? The main technique that we use is that if I want to become a leader, I will take the same Paxos protocol and augment it with one simple addition. I would announce which replication quorum I'm going to use. And by having these announcements, the other future leaders will be able to judge what are the replication quorums that they need to intersect with. So basically, one instance of how we can use this technique is a simple three-step algorithm for leader election. First, I'm going to start with a small leader election protocol that would only intersect with other leader election protocols. So I can use something like a majority of nodes for leader election. Of course, this is different from flexible Paxos, where I need to intersect with all replication quorums. And then, in the leader election phase, I will announce what is the replication quorum I'm going to use. And finally, in this leader election round, I'm going to detect any currently used replication quorums so that I can expand my leader election quorum to intersect with those new ones. So to visualize what's really happening here, let's take this example of 5 zones. So we have 5 zones, each containing 3 nearby data centers. And we want to optimize the performance for replication. So the replication quorum will be 1 for each zone. If I am at zone 1, I want to use a replication quorum that is only local to me. So now if a node in zone 1 wants to become a leader, it will perform a leader election phase that spans only a majority of zones rather than all zones. And in the process, it will send an announcement. I'm going to use zone 1 as my replication quorum. And after that, it won't detect any replication quorums that are being in use, so it will go ahead with replication and perform local replication at zone 1. But now, if a node in zone 4 wants to become a leader, it will perform the same thing. It will pull the votes from a majority of nodes, zone 2, zone 3, and zone 4, and it will announce that it wants to use the zone 4 for its replication quorum. But in this case, what is different is that it detects that there is a replication quorum that is being used at zone 1. So it will go and pull a vote from zone 1 so that it can proceed with the leader election. And after getting the vote and intersecting with that currently used replication quorum, it can go ahead and perform the local replication. And this ensures that there are no conflicts because we know that the local replication that's happening at zone 1 can no longer be used because we already intersected with zone 1. So that's an instance of how the idea of a dynamic expanding quorum can be used. But in the paper, we also show how we can take this idea even further. In fact, we can achieve even smaller leader election quorums that are as small as a single zone. So to know how we do this, I invite you to read the paper or talk to me. I'll be around after the session. But we also propose other ideas that will improve the performance of leader election. So with this, I'm going to conclude the talk, and I'm happy to receive any questions.
So to do leadership election, if you detect that there's an active leader, you need to contact that zone. So do you have the same availability properties as flexible Paxos?
Oh, that's a really good question. And the availability question needs to be integrated in the design of the quorums. So of course, I didn't get into this problem here, but whenever someone is going to use either flexible Paxos or dynamic Paxos, they need to take into account to design the quorums so that the sizes of these quorums will allow tolerating a certain number of failures. So I'm not going to go in details about this, but I think I give you kind of like a high-level idea, but it's all explained in the paper too, if you're interested.
Yeah, so probably a follow-up. So in case of partitions, do you have the conflicts of rights? Because it looks like with micro-localized elections, their nodes are not aware about failures and might take rights on multiple centers. How do you resolve this?
Well, that's another also really good questions. And we deal with this question also kind of like in the same way, which is the design of the leader election and replication quorums. And kind of like to answer your specific scenario of, for example, a data center failure, the replication quorum would have to spend 2 data center or 2 zones in this case. And kind of like everything would follow in the design of the other replication quorums and later election quorums. Something that we do in the paper is that we allow the design to be parameterized. So we expose two parameters, the number of failures that you want to allow in a zone and the number of failures that you want to allow within zones. And kind of like using these two parameters, the quorums will be designed accordingly. Yeah.
Thank you.
You're welcome.
Any other questions? All right, thank you.
Thank you.